Good morning, students. আজি মই তোমালোকৰ আগত CFTৰ সহায়ত লেবাইলিটি আৰু ইনাৰ্টনেছ কেনেকৈ ব্যাখ্যা কৰিব পাৰি সেইটোকে বুজাবলৈ ওলাইছো। মোৰ যোৱাটো ভিডিঅ'ত আচলতে VBT ইউজ কৰি লেবাইলিটি আৰু ইনাৰ্টনেছ এক্সপ্লেইন কৰা হৈছিলে আৰু তাত আমি কিছুমান লিমিটেশনছ দেখা পাইছিলোঁ আৰু সেই লিমিটেশনছখিনি আচলতে দূৰ কৰিবলৈ CFT সহায় লোৱা হৈছিল। প্ৰথমে আমি সকলো এটা কথা জানো যে নিউক্লিওফিলিক সাবস্টিটিউশন ৰিয়েকশন দুই ধৰণে হয়। তাৰ মানে নিউক্লিওফিলিক সাবস্টিটিউশনৰ দুটা ৰিয়েকশন মেকানিজম আমি জানো। এটা মেকানিজম এসোসিয়েটিভ মেকানিজম বুলি কোৱা হয় আৰু আনটো মেকানিজমক ডিসোসিয়েটিভ মেকানিজম বুলি কোৱা হয়। ইয়াৰে যিটো এসোসিয়েটিভ মেকানিজম তাতে যিটো ইন্টাৰমিডিয়েট ফৰ্ম হয় এই ইন্টাৰমিডিয়েটটো 7 কোঅৰ্ডিনেটেড হয়। আনহাতে যেটো ডিসোসিয়েটিভ মেকানিজম এই ডিসোসিয়েটিভ মেকানিজমত যেটো ইন্টাৰমিডিয়েট ফৰ্ম হয় সেই ইন্টাৰমিডিয়েটটোৰ কোঅৰ্ডিনেশন নাম্বাৰ 5 অৰ্থাৎ ই এটা স্কয়াৰ পিৰামিডাল জিঅমেট্ৰি কমপ্লেক্স আয়ন। এতিয়া সেই ইন্টাৰমিডিয়েট গিটাৰ যেহেতু জিঅমেট্ৰি বেলেগ বেলেগ গতিকে তাত তাৰ লগত জড়িত হৈ থকা ক্ৰিষ্টেল ফিল্ড ষ্টেবিলাইজেশ্যন এনাৰ্জি বা ক্ৰিষ্টেল ফিল্ড স্প্লিটিং পেটাৰ্নটো বেলেগ বেলেগ আৰু এই ক্ৰিষ্টেল ফিল্ড স্প্লিটিঙৰ সহায় লৈ আমি এই লেবাইলিটি আৰু ইনাৰ্টনেছটো ব্যাখ্যা কৰিব পাৰোঁ। So as we know that the geometry of both reactants and intermediates different, and therefore crystal field splitting pattern for both will differ. As I have already mentioned that nucleophilic substitution takes place in two different ways. In both the cases, we can see that geometry of both the reactant and the intermediates are different, whether they are associative, going through associative mechanism or dissociative mechanism. Secondly, we know that rate of a chemical reaction depends on the activation energy of the reaction, and therefore it can be correlated with the energy of the transition state. Means rate of a chemical reaction largely depends upon the transition state that is going to involve throughout the course of the reaction. So transition state plays an important role in case of in the rate of the reaction. And one of the factors that include activation energy of the reaction is crystal field activation energy, that is CFAE. This may be a new term for you. Actually, this is nothing but this is the difference of crystal field stabilization energy of the intermediates and that of the reactant. So it can be represented like this: crystal field activation energy is equal to crystal field stabilization energy of the intermediate. Means intermediate of the reaction mechanisms. Like in certain cases, in case of associative mechanism, the intermediate will be a 7 coordinated intermediate. So in that case, we'll have to calculate the CFSE for a 7 coordinate intermediate system minus CFSE of the reactant. So if we are talking about an octahedral system, then obviously we'll have to calculate the CFSE of the octahedral geometry, and the difference between these two systems, two CFSEs, that will lead to, or that will give you the value of crystal field activation energy. And this particular term, crystal field activation energy, will play an important role in the rate of the reaction, and indirectly it will tell you about the lability and inertness of the coordination complex. So first of all, we are discussing about the dissociative nucleophilic substitution reaction of an octahedral system. So this is the mechanism. This is the general pictorial diagram of the reaction. This is the octahedral reactant, and this is the intermediate, 5-coordinated intermediate. Preferably, it will be a square pyramidal intermediate, which is taking place during a dissociative mechanism, and this will be the final product, which is again will be an octahedral system. And now, if you wish to find out the CFA of this compound, then you'll have to calculate the CFSE of this 5-coordinate intermediates minus the CFSE that is obtained for this octahedral system, and that will give you the CFAE of this compound, and that CFAE will play an important role in deciding the rate of the reaction. Now this is the associative mechanism, which involves the 7-coordinated geometry. This is the 7-coordinated geometry. Here, in order to find out the CFAE, you will have to calculate the CFSE of this intermediate minus the CFSE of the octahedral reactant. So that will give you the CFAE of this reaction that is taking place through associative nucleophilic substitution mechanism. So crystal field activation energy can decide about the feasibility of the formation of the intermediate. The difference of crystal field stabilization energy of intermediate and the reactant, as I have already mentioned, that this is nothing but this is the difference of the crystal field stabilization of the intermediate and the reactant in the crystal field activation energy. Crystal field activation energy is one of the important factors among the various that can decide the activation barrier of the reaction. So that I have already discussed. Now, how this CFAE can be utilized for deciding the feasibility of a reaction which is taking place through a dissociative mechanism. For that, as we came across that in a dissociative nucleophilic substitution reaction, and 5-coordinated intermediate is involved, and that's why we have to find out the crystal field splitting pattern for a square pyramidal geometry, and then the crystal field splitting pattern of a regular octahedral complex, because the reactant itself is an octahedral complex. So let us take an example of a D1 system. D1 system means the complexes in which a metal ion contains only one electron in the outermost cell D orbital. So this will be the situation. This is the degenerate 5d orbitals, and this is the only electron present in the system. And in an octahedral field, initially in the reactant, it means in the reactant, the electron will preferably occupy the lower line T to the set of orbital, one of the T to the set of orbital. Since only one electron is there, that is obviously it will go to this side. Now on the other hand, in an intermediate system, the lone electron will go to the lower line dxz or dyz orbital. These are the two degenerate orbital found, lowest energy degenerate orbital found in the square pyramidal geometry. So before knowing this, you will have to know the exact pattern of a square pyramidal geometry or a 7-coordinated complex geometry, crystal field splitting patterns. So after knowing only, you will be able to find out the exact value of CFSE for this particular geometry. So these are the values. So these two degenerate orbitals for square pyramidal geometry will have minus 4.5 dq for each of the electron. Next is minus 0.9 dq, which is a dxy orbital, then dz square orbital plus 0.9 dq, and the highest energy orbital will be the dx square minus y square orbital, which 10 dq value of 9 dq, 9 dq. The delta O value is, sorry, not delta O here, here is only delta sp, means square pyramidal. So in that case, it will be 9 dq. Now, on the basis of different factors that affect a crystal field spinning as a formed complex may either be high spin or low spin. So there are two possibilities depending upon the size of the metal ion as well as the nature of the ligand that is present or that is associated with a particular complex. We can have a high spin complex or a low spin complex. So CFAE will decide about the lability and inertness of the complex. More negative the value of CFAE, more will be the chances for formation of the intermediate, and therefore more labile complex will be. Means after calculating the CFAE for a particular complex, more negative value of the CFAE, more will be the chances of for the formation of the intermediate, and therefore more labile complex will be. So in this way, you will have to find out whether a given molecule is a labile, given complex is a labile complex or a inert complex. So this is a table which is showing the CFAE for different electronic configurations D1, D2, D3, D4, D5, up to D10. So here for D1 system, you can see the CFSE for the octahedral reactant or the starting material is found to be 4 dq. Whereas the intermediate, since it is a dissociative mechanism, this is going to the dissociative mechanism and it's a high spin one. So it will have the CFAE for a square planar intermediate will be minus 4.5. And the difference between these two is come out to be minus 0.5. Since it has a minus CFAE value, negative CFAE value, so it will be a labile. Similarly, for a D2 system, CFSE for the octahedral reactant will be minus 8, since both the two electrons will go to the lower lying T2Z orbital. Each of them carries minus 4 dq. So since 2 electrons are there, so total CFSE value will be minus 8. On the other hand, CFSE for the square planar complex with 2 electrons will be 9, as can be seen from the earlier figure. Here you can see 2 electrons. 2 electron means this dxz orbital will also be filled up. So 1 electron is equivalent to minus 4.5. So 2 electron means minus 9. So in that way, we'll have to find out the corresponding CFSE values. So here you can see the difference between CFSE for the square planar and the CFSE for the octahedral will be minus 1. Here also it is a negative value, so it will be a labile complex. Now, if we look at the D3 configuration, then the CFSE for the octahedral will be minus 12, and the CFSE for the square planar geometry will be minus 9.9. Here you can see that the CFAE value comes out to be a positive value, that is equal to plus 2.1. Since it has a positive value, so it will be an inert. D4, likewise the D4 system, for D4 minus 6, CFSE for the octahedral is minus 6, CFSE for the square planar is minus 9, and the CFAE for DQ, CFAE for that system is minus 3. Since it has a negative value, so it will be a labile one. So this is possible only when, while talking about a D4 system, this is the situation when the complex is a high spin complex. Means the fourth electron enters to a d z square orbital, then only it is possible. Otherwise, it could have fared with the lower lying orbital. So in that case, it will be a different one, as we are talking about the high spin complex. Then D5 CFS will be 0, CFS square planar is also 0. So 0, it means it is level. Then D6 minus value, negative value, level. D7 negative value, level. D8 positive, so it is inert. D9 negative value, so it is level. So out of this 10 system, I think these two, D4 and D9 system will be the most level, highest level complexes, because they are carrying more negative values as compared to that of D2 and D1. They are having negative. They are also having negative values, but they are lesser than D9 and D4, which are having -3 in each of the case. So similarly, we can move to low spin complexes. Low spin complexes means the complexes in which the ligands are very strong ligands. The energy gap between the orbitals is very much high, so they cannot go to a high lying orbital. Instead, they will prefer to pair with the lower lying orbitals and giving rise to a low spin complex. So in this case, you can see the D1 system. For D1 system, it is similar to that of the high spin complex. So here also it comes out to be -0.5, which is a level one. Then D2 is also level. D3 is inert. As in the case of your high spin complexes, then D5, D4 is inert. D4 with plus 1.6 value is also inert. D5 with plus 1.1 is also inert. D6 plus 4.2 is also inert. D7 negative value, it is level. D8 positive value, inert. D9 -3 negative value is also level. So among these, we can see that the D9 system with -3 highest more negative value will be the most level complexes among these, and D6 system with highest positive value plus, that is plus 4.2, is the most inert among these complexes. So now let us move to the associative nucleophilic substitution reaction. So as I have already mentioned that in this type of reactions, in these mechanisms, a 7 coordinated intermediate is being formed, and for which also we'll have to know the crystal fill stabilization energy. So I have not been able to show you the crystal field splitting pattern, but still we can remember this table. With the help of this table, you can find out what is the exact CFAE value for a particular electronic configuration. D1, the difference is -1.3, that is level. D2 -2.6, which is also a level. But D3 is inert with positive value 4.25, D4 plus 1.1 inert, and so on. So I think it will be helpful. This table will be helpful to find out which what are the level complexes, which are the level complexes, and which are the inert complexes on the basis of their electronic configurations that they involve. So let us come to the summary of this video. Crystal field theory explains the concept of lability and inertness on the basis of crystal field activation energy, which is the difference of crystal field stabilization energy of the intermediate and the reactant. For SN1 reaction, complexes containing metal ions with D3 and D8 arrangements are inert in both their low spin as well as in high spin state. while D4, D5, and D6 arrangements are inert in low spin states only. On the other hand, for associative nucleophilic substitution reaction, complexes containing metal ion with D3, D4, D8, and D9 arrangement are inert, while D3 to D9 configurations are inert for low spin complexes. So I think it will help you in understanding the concept of lability and inertness. If it is possible, I will try to make some other videos regarding your other topics. So thank you.